Thank you very much for inviting me. So today I'll talk about distributed statistical estimation of matrix products. So this is a joint work with Woodruff. So we work in the standard communication model. So we have two parties, Alice and Bob. Alice has a matrix, Bob has a matrix, and they want to compute some function on the product of these two matrices. And our goal is, again, to minimize the communication cost and also the number of runs of the communication. So we consider a set of statistical problems. The first set of problems is p-norm. So what we want to compute is just the p-norm of the product of the two matrices. Okay? So when p is equal to 0, this is simply the number of non-zero entries of C. And this problem actually corresponds to the size of set intersection join in database. So if we think each row of A as a set and each column of B as a set, so our goal is just want to compute the number of pairs AI, Bj that they intersect. Okay. So when P is equal to 1, this corresponds to the sum of the entries of C. It's basically, if in the database setting, it's the size of the corresponding natural joins. And so I want to say that these two problems, the set intersection join and the natural join, they are arguably the most important operations in relational database. These people really cares a lot. And the size estimation is the key to query optimization. Okay. So basically, we want to spend very few resources to try to estimate the size. Then we can build the operation tree for more complicated operation database. Okay. So when P is equal to infinity, this is just the maximum entry of C. So this corresponds to the most similar pair AI and Bj. So I just want to show you like application of set intersection join. So this is an application in job. This is a scenario of job application. So we have a set of applicants and a set of openings. So each applicant has a set of skills, and each opening requires a set of skills. So what we want to do is find all the candidate applicant opening pairs that they intersect. They have a common skill. Okay. So we will recommend those kind of pairs for interview, for example. Okay, so this is just one application of set intersection join. Okay, so we also study the problem of heavy hitters. So here, basically, just want to output all the entries of C that is larger than some threshold phi times the p norm of C. So often, like we cannot compute this exactly, so we just target for an approximate version of this. So basically, we want to output all the Cij's that are bigger than phi times the p norm of j, and do not output anything that is smaller than phi minus epsilon fraction of this of a p norm of C. And for those in between, we don't care. Okay, so this corresponds to the similarly join in the database setting. Okay, so again, this is also like the very important problem in database. Okay, so let me show you our main results. So for simplicity, let's assume like we are working on square matrix, so M is equal to N. Okay. So for p-norm, so what we get is a two-round algorithm using N over epsilon bits of communication up to some Poilog factor. So we can approximate the p-norm of the product of these two matrices with the effect of 1 plus epsilon. Okay. So for p equal to 0, this improves the previous result. So we have a paper a bit earlier with Dirk, Ryan, and David. So we got the upper bound N over epsilon squared. This is actually a very simple, almost trivial algorithm, like use aerial sketching. So it's very simple on each column of C. So we improve this by a factor of epsilon. Okay, and the same paper gives a lower bound N over epsilon to the power 2 over 3. Yeah, I will talk about some ideas how to get this lower bound in a few slides. And if we restrict the communication to be one way, then this is actually optimal. So this result, our result shows a separation between one-way communication and the multi-round communication for p-norm estimation. Okay. So for L infinity, what we get is a constant round algorithm that approximate L infinity within a factor of 2 plus epsilon using n to the power 1.5 over epsilon bits, still up to, again up to some polylog factors. And for general approximation factor, we get a similar result, n to the 1.5 divided by kappa. Kappa is the approximation ratio. Okay, so we can show that these results are actually close to optimal. So we show that if we want to approximate this within a factor of 2, then basically we have to send everything. So n squared is the lower bound. If we want to approximate within a factor of kappa, then basically this result is tied up to some log factor. Okay. So these are all for binary matrix. So if a matrix, general matrix, take arbitrary integer values, then the bound is actually much higher. So it's n squared over kappa squared. Kappa is the approximation ratio. Okay. So this is for L infinity. So for heavy hitter, for binary matrix, we get constant, again constant round, and communication is n plus phi over epsilon squared. And for general matrix, it's slightly higher. So basically, it's two things multiply. Okay, and all of these are for square matrix. And for rectangle matrix, means that those results can be easily extended to rectangle matrix. Basically, just replace some of the n, not all of them, some of the n to n. Okay. Okay. So so these are our results. So let me briefly mention like what previously. What results are known previously. So as mentioned, like our earlier paper studied the L0 norm of the product. So there are a number of papers looking at distributed linear algebra problem, but the focus is on the compute some statistics on the sum of the two matrices instead of the product of these two matrices. Okay. Question? And these similar problems have been studied in RAM model. So there's quite a few papers on the RAM model. But surprisingly, I think it's a very simple, clean problem. Not much work has been done in the distributed model. Okay. So this is all I know. So in the rest of the talk, I will give you two simple algorithms for L infinity and L0, and I also mention some. Did some ideas on the lower bound proofs. Okay. So let's start with 1 plus epsilon approximation of the L01 norm. So here's a high-level idea. So what we do is we first perform a rough estimation of the number of non-zero entries of the result matrix C, and then we use this rough estimation to partition the rows of the C to groups, so that rows in the same group have similar number of non-zero entries. And then we sample the rows in each group with probability proportional to the estimated average number of non-zero entries of the rows of the group. And then we use those sampled rows to estimate the number of non-zero entries of C to a more accurate level. Okay. So how to implement those things? So this is the actual implementation. So we have two parameter beta we set to be square root epsilon. Epsilon is approximation factor, and rho is we set to be 1 over epsilon. So let's assume that communication starts from Bob. So we use the previous algorithm, basically like a simple linear sketch, to get the 1 plus beta approximation of the number of non-zero entries of the rows of each rows of C. Okay, and then Alice, after getting this information, Alice can partition those n rows of C. This is the estimation of C to a set of groups, log n over beta groups, so that the rows in each group they have similar number of non-zero entries, and then for each group, basically Alice just sample each rows with a probability like proportional to the average number of non-zeros of the rows in this group. This is just a normalization factor. And then let A prime to be those sample rows. We can pad others by 0. And then Alice send those sample rows or the sample matrix A prime to Bob, and Bob just compute C prime that is product of A prime and B. Okay. And then after getting the C prime, so Bob can compute the number of non-zero entries of the rows of C prime, then properly rescale and then sum up. So that's we can show that this is an unbiased estimation and the variance is small. Okay. And the number of the communication cost is basically, so communication happens here in step 1 and step 3. So step 1, so basically it's directly from the previous result, so it's n over beta square. So we set beta square to be square root n square root epsilon, so this is 1 over epsilon. Okay, so we cannot so previous result just directly sets beta equal to epsilon, so this is why we have n over epsilon square. But this is too much, so we have to use like a larger approximation ratio. This is what do I mean by rough estimation. Okay, and this step takes. So because, so this step also takes n over epsilon bits of communication. Okay, so this is basically the upper bounds. So I will talk about lower bound. So this lower bound is actually in our previous paper. For proving a lower bound for this problem, let me first introduce two primitive problems. The first is the well-known set disjointness. I guess probably all of you knows. So we have Alice and Bob, and each of them have a n bits vector, and they just want to see if they have coordinates that both xi and yi are equal to 1. Okay? And exists some hard input distribution that under this solving this problem with good probability needs omega n communication. So this is a well-known result. And the second component is also kind of widely used primitive problem called gap hamming. So again, like we have two parties, each of them has n bits vector. So let wi to be the XOR of xi and yi. So our goal is to determine like whether the sum of those wi is less than n over 2 minus square root n, or bigger than n over 2 plus square root n, and in the middle we don't care. Okay, so again we can show that there exists some hard input distribution that solving gap hamming with a good probability needs to learn. So it's slightly different. We need to learn at least a linear number of wi's with a well. By well means the mutual information between wi and this protocol transcript is at least omega 1. So this is what do I mean by learn well. Okay? So this is two components we use. And then, so this is the hard input distribution for the L0 estimation problem. So I will set the value of m shortly. But so basically, for each for each pair AI BI, this is chosen as an instance of the hard. So it's chosen like an instance of the set disjointness problem, and according to a hard input distribution mu. Okay? And then we define the sum of AB to be just a sum of the output of this M set intersection join. And then we can show that with high probability, the L0 norm of of AB is equal to the sum of the sum AB plus this actual term, roughly M squared. Okay, and then so we can show that it's hard to approximate this sum AB within a small error. So what we do is we can show that any randomized algorithm that computes this sum with probability 0.99 up to an additive error square root n we need to spend like omega m times n communication. Okay, so yeah.
Yes, I got lost in something.
Okay.
So what happens with AI and BJ? I mean, they don't have any relationship between them, right? So you're taking the product of AI and BJ. That's definitely counted in the.
So the counted is this term, yeah. So this term counts. You will see in next slide. Yes, it will count. So this term counts like the AI and the BI, and this term counts AI and the BJ not equal to I. So this is why we have this. So we have like m rows and m columns. So this is basically every A and Bj will kind of intersect under our hard input distribution. Yes, yes. So this is where you add this term. Sorry, I should mention this. Yeah. Okay, so how to prove this? Basically, the high-level idea is that, okay, to approximate this sum well, we have to solve embedded gap Hamming instance. And by previous lemma, to solve this gap Hamming instance up to additive error of square root m, we have to learn basically linear number of the bits wi, and each wi is the output of a set disjointness problem. So that means if we want to solve, basically we have to solve this set disjointness problem, which needs omega m bits. So these two terms multiply. So this is why we have m times n. But the actual analysis, actual arguments are actually more involved. Like we have to modify the distribution for set disjointness and gap Hamming to make sure that they can compose. And we even have to modify the definition of those problems a little bit. But those are details that I don't want to really get into. But this is high-level idea. Okay. And then we set m to be this value, 1 over epsilon to the power 2 over 3. To make the arrow square root m to be epsilon times the L0 norm of the product of the two matrices. Okay, so this gives us this lower bound. Okay. So this is a high-level sketch of the lower bound proof. So if you want to only remember one slide of the talk, this is the slide. So the main question left by our work is the following. So we have upper bound of, sorry, I should put tutor here. So, but if you don't care log factors, then it's n over epsilon. And lower bound is n over epsilon to the power 2 over 3. So question is like, which one is the right complexity? Maybe none of them is. So maybe there's something in between. So we still don't know. We spend a lot of efforts trying to improve this upper bound. But so far we haven't succeeded. But on the other hand, like lower bound, this 2 over 3 looks like a bit weird. I've never seen like such power like 2 over 3. So I don't know like which one is the case. So the difficulty here is like we cannot set this m to be larger than 1 over epsilon to the power 2 over 3 because like under the harder distribution we choose, exactly what I mentioned. So each AI will intersect with each Bj, j not equal to I, so with high probability. And this term, if we set this m to be too large, then this term will dominate the L0 norm of the product of C. Okay, and I mean this is probably I mean, I would like to think is like okay. On this scenario, the primitive problems overlaps. I mean, overlap is probably not the best word to describe this, but this is how I I have in mind, the picture I have in mind. So, and I guess maybe like if you want to prove this higher lower bound, maybe some new techniques.
So, yeah. Question. So, this n over epsilon squared is a bound that holds even for one way, right? Or that's the bound you get for one way, isn't that right?
N over epsilon squared, that's for one way, yeah, that's a tight.
But then these two problems, if you sort of, I mean, I'm trying to understand where's the difference between one way and two way comes in because these lower bounds seem to be working in either model. So what am I missing? The gap Hamming and disjointness. Oh, I see, they give a weaker bound of n over epsilon to the 2/3 even for one way. Is that what happens? So you have a
yeah. So for one way, like if you use these things, I mean, you can still use these things. So these things works for unbounded number of rounds, right? So you can still use it for one round, but you get worse lower bound.
I see.
Not. No. Yeah, you got worse lower
bound. Why is it that you can prove a better lower bound for one way, but not for?
One way we don't use this.
Okay.
Yeah, we use something else. Yeah.
I see.
So okay, so let's move to L infinity. So for L infinity, we prove like two. We've got the algorithm for 2 plus epsilon approximation. So So here's the idea. So the idea is to try to sample this matrix C. So by sample, I mean the following. So actually, we cannot sample directly on C. We sample on A. Basically, we create like a hierarchy of sample the matrix A1, A2, A3. So A1 is like we sample every entries of A with probability 1 over epsilon, and which is a hierarchy. And C1, C2 is just this product of A1, B, and A2, B, and so on. Okay. So we keep doing this, and our idea is to try to subsample C to a level L, such that first L, we hope L to be as large as possible. In other words, the L1 norm of CL to be as small as possible. Because if this is very small, then you will see like what happened in the analysis. And then on the other hand, the L infinity norm of CL is still a good approximation of the L infinity norm of the original matrix C. Okay, so this is a high-level idea, and let's see like how we implement this. So it's actually very straightforward. Again, we have two parameters. This is total number of levels, and this is a parameter we use like in the second step of the algorithm. So the subsampling can be done in one pass. So Alice just sample A and send some information to B and Bob, and Bob can compute those CLs actually exactly. And the communication cost for this is actually very small because because basically what Alice do is just so for AL, Alice don't have to send the whole AL. Just send the number of ones of each column of AL, then that's enough. So it's kind of almost linear. Okay, and then what Bob do is Bob compute this is local computation, right? So Bob got all the CL, C1, C2, C3. So it can find the L star, that is the smallest L, for which the L1 norm of CL is no more than gamma times n squared. And then we focus on this particular level L star. What we do then is, so we look at these two matrices, A, L star, and B. So let Uj to be the number of ones of the jth column of A, L star, and the Vj to be number of ones of the jth row of B. And then we compare these two values. If Uj is less than Vj, then Alice send the whole row to Bob, and to the jth column. Sorry, the jth column of A, L star to Bob, and otherwise Bob sends the jth row of B to Alice. And then use those after this exchanging of rows and columns, and they can compute two matrices. So they can compute the CA and CB respectively, so that the sum of C and CB is equal to CL star. Okay, and then they output a max of so Alice can compute the L infinity norm of CA, and Bob can compute L infinity norm of CB. Then properly scale, then they turn the max of these two. Okay, so this costs one round. This is local computation. This costs 2 rounds because Alice also need to know what is L star, right? And then the last line costs 1 round. So in total, it's a 4-round protocol. And so correctness is actually very simple. So first, we can show that if we look at this particular level, we can show that the L infinity norm of CL star after proper rescaling is a good approximation of L0 norm of the original matrix C. And then this is like what we have, right? This is what we have. This is a simple fact. So that means max of this 2 is a 2 plus epsilon approximation, 2 approximation of the L infinity norm of CL star. And combine these 2 facts, we get 2 plus epsilon approximation. Okay. So this is the correctness of the algorithm. And the communication cost is actually dominated by the exchange of those in rows and columns. So we analyze this cost by 2 cases. The first is like both this number of ones in columns and the number of ones in rows. Basically, both Uj and Vj are large, but we can say that means there are not so many J's because the L1 norm of CL star is small. Because just to J will contribute like Uj times Vj mass to the L1 norm of this matrix. So if this is small, then there are not so many J's, so the communication is bounded. Otherwise, it's even simpler, right? So because one of them are small, so that means like the amount of information we send is small. So this is a high-level idea, and we can probably balance those things and get this n to the power 1.5 over epsilon. Okay, so that's basically the analysis. So very quick proof of the lower bound. So this lower bound is actually very simple. So we are going to prove a lower bound for L infinity of C. So it's basically a simple reduction to set the set disjointness. So what Alice has is X is a n square over 4 bit string, and Bob has is also, again like n square over 4 bit string. So what Alice do is partition this bit string to n over 2 chunks, each of size n over 2, and then use it to construct a matrix A prime of dimension n over 2 by n over 2, and then we construct this block matrix. So A prime is just the one of the component, and this is an identity matrix, and this is to basically zero matrix, and the dimension of A is again n by n, and the same thing, similar thing to B. So Bob 0 is here, so B prime is in the left button, okay, and then we can show that the L infinity norm of the product of A and B is equal to the L infinity norm of the sum of A prime and B prime. And which is true if the disjointness returns 1 and the 1 otherwise. So this is a whole reduction. That means like you cannot really approximate things better than or equal than 2. So that's it. So let me wrap up. So this recap. This is the main results of the paper. So 1 plus epsilon approximation of the P norm of the product of matrix using n over epsilon communication in the 2 rounds, and we got for L infinity we got the 2 plus epsilon approximation using n to the power 1.5 over epsilon, and the communication takes 4 rounds, and there are some other results for heavy hitters, which I haven't talked about. So there are couple of open problems. So this problem I already mentioned. So I want to close the gap between upper bounds and lower bounds for L0. And so for L infinity, so this protocol cost 4 rounds. So again, I don't think like 4 is the right bound. So why rounds is important because especially in practice, starting a round is very expensive. People really want like 1 round or 2 round communication. So if you talk to database people, I need log n rounds, they will not be interested. So even 4 rounds is a bit expensive. So can we reduce this to 2 rounds, for example? And for heavy hitter, we only get upper bounds, and we haven't thought about lower bounds. So everything is open. Okay, so I think that's all I want to say.
Josh? So you have this 1 round lower bound which is dependent on 1 over epsilon squared. Are you aware of any other problems where the dependence on epsilon on this approximation factor is related to the number of rounds of communication?
So here, like basically, we show like 1 round or 2 round are different, but if you ask like, okay, is there any result has a round as a parameter in the communication lower bound?
I don't mean as a function of number of rounds.
Okay.
I'm fine with like 1 round versus
2 rounds.
Bidirectional communication or 2 rounds.
I think for L infinity we didn't prove, but I think there's also a separation. Yeah, in general, like 1 round versus multiple rounds, I think there should be a lot of results on this.
It's thanks, Jim, again.